Okay, so today we are going to look at the module number three, sorry, module number three LEDs. But in the LED module, we are going to look at a special type of laser diode called as indium gallium nitride on gallium nitride substrate laser. Okay, the importance of this laser diode is that it is a blue laser, and actually the technology was developed very recently because green and red lasers were very popular in the olden days, and it was very difficult to fabricate a blue laser. Finally, although there are some defects and problems in developing this blue laser, you will finally get a blue laser using indium gallium nitride laser diodes. Okay, so objective of this lecture is to understand the construction and working of indium gallium nitride laser diode, and we want to also understand the characteristics of indium gallium nitride laser diode. Okay, so let's look at the band diagram. Okay, and the structure. So we will explain the structure in detail in the coming slides. So if you look at the structure, you can see that it is a sapphire substrate. It need not be always sapphire substrate. So the laser, indium gallium nitride laser, can be fabricated using different substrates. This is a multi-quantum well laser, and there are lasers, indium gallium nitride lasers of different kinds. So the most commonly used is with sapphire substrate. And if you look at the layers, you see there is a gallium nitride buffer layer. We'll see why all these layers are there. And then there is N-type gallium nitride layer, or which there is N-type gallium nitride layer with composition 0.1 and 0.9. And then there is aluminum gallium nitride layer, which is this one, with composition 0.15 and 0.85. There is N-type gallium nitride layer, and there is an active layer of this. Although you see that the active layer is like indium gallium nitride multiple quantum well, there are multiple layers inside the quantum well or in the active region. This we will see in the coming slides what are those layers. And then we have aluminum gallium nitride. There's a gallium nitride p-type. There's a p-type aluminum gallium nitride. There's a p-type gallium nitride layers. Okay, so these are different layers of this device, and there is a metal contact at the top and at the lateral entry. And there is a p electrode and n electrode, which is basically connecting to this metal. Okay, so as you know, in lasers, the basic principle is there should be a population inversion, there should be a optical confinement, there should be an optical feedback, and there should be an amplification media. So all these layers, different layers, serve one of these purposes. So there is a guided medium, which is because of the p-type gallium nitride. There's a confinement because of p-type aluminum gallium nitride, and there will be some kind of a cleaved structure at the side of this laser diode, which will reflect the light to give you the proper lasing action. Okay, now if you come to the band diagram, so this band diagram is tilted sideways. Actually you would have drawn energy here. This should have been energy and this should have been X. Okay, but this band diagram is tilted up in sideways. We'll see the tilted band diagram also, but you see there are multiple quantum wells here. Okay, so this is quantum well. Okay, and there are, since there are at least two or more than two, we call as multiple quantum well, MQW, which means it's a multiple quantum well. And there's a big barrier here, you see, here and also here. We'll see why these barriers are there, and there are the different layers. Right. So this is the tilted structure. This is a normal structure that we see or we draw in our classes. So you see that there are periodic quantum wells here. Okay, so there is a periodic quantum well. Periodic quantum well means it is repeating at regular intervals with the same width quantum well. Okay, and we see that actually this is shown only two. There are actually 26 of them. And then if you move forward, you see that there is a big barrier because of aluminum gallium nitride, which actually helps in the confinement of carriers, because you see that when you apply an injection current, the carriers at the conduction band, which is mostly electrons in the conduction band, will move down into the quantum well. Okay, and it will stay in the quantum well because the barrier here is pretty large, so it cannot move out of this quantum well. Even if there are carriers here, okay, because of this large quantum barrier, okay, the carriers cannot move out. So the carrier is confined inside this quantum well, which will increase the emission rate. So you will have more number of carriers, which finally give you a population inversion, since the carriers cannot climb the quantum barrier of this large well here. So more carriers will be confined inside the quantum well, and they will start giving radiation by if you give a simulated photon. So that's why we have big quantum barrier. And also the released photons due to stimulated emission will not be absorbed by any of the other layers because the band gap of the other layers are high when you compare to the band gap of the quantum well. So those are the two advantages of having such a structure. So let's look at the construction. So the first layer is the sapphire substrate. Okay. So this is a heat substrate in hydrogen stream. So what you do is you have a sapphire wafer, then you heat it in hydrogen stream at 1050 degrees Celsius. Okay. So that is your first layer. The second layer is gallium nitride buffer layer, that is here. Okay. So that is rolled out over the substrate by heating it at 550 degree Celsius, and the thickness of the layer is 300 Angstrom. 300 into 10 raised to minus 10 meter. That's 300 Angstrom. Okay, so you have gallium buffer layer, and then you have N-type gallium layer, which is the bigger layer over the gallium buffer layer. Okay, again that is substrate temperature is about 1020 degrees Celsius, that is heated, and the thickness is 3 micrometer. Now there is the next layer, which is on top of N-type gallium nitride layer, which is indium gallium nitride layer, which has 0.1, 0.9 composition. Now why we need this layer is it's actually a buffer layer. The problem is, like, when you have aluminum gallium nitride, which is the next layer that is coming up, grown over N-type gallium nitride, it will crack the aluminum gallium nitride film. So basically, aluminum gallium nitride and gallium nitride will not go easy or will not go together between them, and they will cause problems in either of the layers if you try to construct aluminum gallium nitride layer over gallium nitride layer. But indium gallium nitride layer and gallium nitride layer, or indium gallium nitride layer and aluminum gallium nitride layer, they will easily stick together. Okay, so what you do is you create a layer of indium gallium nitride, which is of N-type, over N-type gallium nitride. Okay, so that once you grow aluminum gallium nitride layer over this indium gallium nitride, it will stick to indium gallium nitride. So that's why you have an extra layer there. Okay, and the length of the layer is 0.1 micrometer. Okay, so after indium gallium nitride, which is of N-type, you have an N-type aluminum gallium nitride layer, which is basically the cladding layers. Okay, so there is an N-type aluminum gallium nitride layer here, which is the cladding layer. So there is also a P-type aluminum gallium nitride layer here. So basically, those two layers will act as a cladding, which will make sure that there is an optical confinement, that okay, you the light which is emitted by stimulated emission will not go or will not get reflected out, like it should be reflected in, or it should not get transmitted out. Okay, so that confinement is done by this aluminum gallium nitride layer, which is of thickness 0.4 micrometer. The next layer is N-type gallium nitride layer, which is this one. This is a light guiding layer. Okay, so what light guiding layer is, like basically you have this active region here, and you want the light to come out of this here in through this active region. Fine. So you should make sure that whatever layer is there in which the active layer has been formed, you should not transmit light to that layer. Instead, whatever light is incident on that layer should be reflected back, and it should get total internal reflection, so that finally the light will move out of the active layer. So this guiding or this wave guide is actually formed because of this gallium nitride layer, which is just below and above the Indian gallium nitride active layer. Okay, so that is the layer 6, which is the gallium nitride layer, is a light guiding layer. And then we have the active layer. So active layer is where we have all the actions in which you have the quantum wells that we have seen in the first few slides. There will be population inversion when you give some current injected through the electrode. The current will flow through the device. It will cause population inversion. When you give a stimulated emission, when you give a stimulation by giving a photon, there will be stimulated emission, and the stimulated emission will cause more optical amplification and reflection, and that keeps on growing in a resonant cavity kind of thing. Okay, so this active layer, although this is shown as a single layer, this is actually a 26-period super lattice. Okay, so we'll see what a super lattice is in the next slide. And along with this super lattice, you have a quantum well layer because of indium gallium nitride 0.2 and 0.8 composition. There's a quantum barrier layer, which is of indium gallium nitride of 0.05 and 0.95 composition. So quantum well layer is where the population inversion is happening. And in quantum barrier layer, it will make sure that the carriers are confined. The carriers will not move out of the quantum well, so that you will have population inversion. Okay. So what a super lattice is, so a semiconductor super lattice is a periodic structure of two or more semiconductors of significantly different band gaps, such that multiple quantum wells are formed in the low band gap layers. Okay, and the layers have to be thin enough to allow carrier transport by tunneling to take place. So basically, you will have some kind of a quantum well here. Okay, and then you will have another structure, something like this, where the band gap is completely different. So if you draw the valence band also, you see that it is something like this. Okay, so the band gap here is totally different from the band gap which will be coming here or here. So, and also this is a periodic structure. Actually, this whole thing can be repeated again. This is called as a super lattice. And why do they form? So that there will be confinement of the carriers inside the quantum well. And because of this confinement, of because of the barrier here, the carrier cannot move out of the barrier and go to the other layers. And also, since more carriers are there inside the quantum well, it can tunnel through the quantum well. So tunneling of the quantum well, we have already seen that when you have a potential applied to the quantum well will tilt, and there will be energy levels common to different quantum wells so that the electron can tunnel through the quantum well. That we have seen earlier. So this superlattice, or which consists of the different band gap layers, which is a quantum well and quantum barrier, will make sure that carriers are confined inside the quantum well, and it is and carriers can tunnel through the quantum well to create the emissions. Okay, so that is the superlattice. And after the superlattice structure, you have the next layer, which is of aluminum gallium nitride. And the reason why we are having this layer, which is this one, is to prevent dissociation of indium gallium nitride layers during the growth of p-type layers. Okay, so ideally we should have the p-type gallium nitride over indium gallium nitride because you already have the n-type gallium nitride here. So ideally you should have, instead of p-type aluminum gallium nitride, you should have p-type gallium nitride. But the problem is, if you develop p-type gallium nitride over indium gallium nitride active layer, the p-type gallium nitride will get decomposed. Basically, the properties of p-type gallium nitride will get removed. It will be a completely, you can say this, it kind of get decomposed, and that will cause problem to our complete structure, and the basic principles for laser will not occur. So we should have an aluminum gallium nitride to make sure that the p-type gallium nitride layer will stick to the device. Okay, so this extra layer is for that purpose, which is layer number 7. And then you have the p-type gallium nitride layer, which is the light guiding layer, which we have already seen along with n-type gallium nitride layer. So this guides the light because it is the layer just above the active layer, which will make sure that there is some kind of a total internal reflection, and it will guide the light. And then over that there is a cladding layer for confinement of light. Like, it will make sure that light will not be traveling outside the device. So that is this cladding layer, or a confinement of light emitted from the active region of the indium gallium nitride multi quantum well structure, which is this layer. Okay, and the last layer is p-type gallium nitride, which is of this layer, which is basically of as a complementary or opposite polarity of our outermost layer, n-type gallium nitride. Right. So these are the different layers of the laser diode, indium gallium nitride, and each layer has its own importance. So make sure you understand why these layers are there in the device. So once you have all the layers assembled, then you can create the metal contact. So this is basically metal, so that you can connect an external circuit and give inject current. So in this case of indium gallium nitride laser diode, there is something called as a pulsed injection. So pulsed injection current means that you might not be supplying a continuous current for all the time. Instead, you will be turning on the current for some time, turn it off, turn it on again, turn it off, turn it on again. So it will be kind of a pulsed way. Okay, so pulse means like on, off, and goes like that. So the current supplied will be in this form so that you will get the proper stimulated emission and you will have the laser action. Okay. And the electrode, which is used for metal contact, is constructed by using a nickel or gold contact, and it will be constructed by evaporating the nickel and gold contact over gallium nitride layer or titanium or aluminum contact on the N-type gallium layer. So this is titanium or aluminum, and this is nickel or gold. Okay, so that is regarding the construction. Now let's look at the working. So working of this laser is pretty same what we have studied for other kind of lasers. So for low injection currents, light is emitted incoherently in a way that is similar to LED case. That is, if you are not supplying enough current, then it will be a normal spontaneous emission. Now, in order to reach lasing action, one need to supply a sufficiently high concentration of carriers within the active region, which is necessary to induce the population inversion. So to create a population inversion, you need to increase the carrier concentration. That is done by supplying a high amount of current. Under sufficiently high excitation, an avalanche-like process of photon-simulated optical recombination takes place, and the device acts as an optical amplifier. So avalanche means you might have seen in films where one small change creates a huge change at the end. Okay, so one change creates another two changes. Two changes will create another four. Four will create eight. Eight will create 64 and goes on. So this is called as an avalanche. So one small excitation using a current will create avalanche number of carriers. And this will finally, if you give a single photon to excite the carrier, it will create two new photons, which will create four new photons, which will create another 8, 16, and goes on like that. So that avalanche kind of thing will happen. So this diagram is basically same as that of the band diagram that I have shown previously. Same thing, you have the high layer of the quantum barrier, and then you have the quantum wells where you have the charge carriers. Okay, so in gallium nitride laser, there's an independent confinement of injected carriers and emitted photons because of separate confinement heterostructure resulting in high optical amplification. So there's a confinement of carriers, which is basically inside this well. The carriers are confined. Confined means it is not able to come out of that barrier. It's basically because of the separate confinement heterostructure, because you have confinement all along the wells here, and also along confined along this because of this barrier. So there is a separate confinement heterostructure which results in high optical amplification. Why? Because each photon created creates two new photons inside the structure itself. Okay, and it keeps on amplifying. The active layers consisting of series of thin Indian gallium quantum wells, Indian gallium nitride quantum wells, and quantum barriers serves as carrier confinement layers. This is that we have already seen. They are sandwiched between N-type and P-type gallium-based optical waveguide. So there is an N-type gallium nitride here and a P-type gallium nitride here, and this is like an optical waveguide. Waveguide is a structure which will guide the wave. So it will make sure that the whatever light laser is action has performed is it will be guided through the medium. It will not get obscured. The aluminum gallium nitride or gallium nitride superlattices are used as cladding layers for an optical waveguide. Okay, so the aluminum gallium nitride will be used for as a cladding, so that you have a totally different refractive index for aluminum gallium nitride or gallium nitride, which will make sure that it is like a cladding. Like it will make sure that the light which is being produced will not be taken out directly. Now, due to an increased excited carrier concentration, the probability of radiative recombination also increases. We know that there can be a radiative or non-radiative recombination. The non-radiative recombination is because of phonons. As the carrier concentration increases in the higher energy level, the probability of radiative recombination increases because you will have population inversion. Okay, so that will be make sure. Emitted photons are effectively guided in a transverse direction by a proper refractive index profile, which is high in the vicinity of quantum wells and decrease in the direction away from the active region. So basically, this is your active region. And this graph shows the refractive index along with the distance. So as you travel along the semiconductor, you see that the refractive index is maximum along the active region, which will make sure that none of the light emitted out of the active region will not be transmitted. Instead, it will be reflected back. Okay, so it will come out and it will see a raw refractive index along the active region, which will make sure the light will be guided and transmitted. The resonant cavity established by reflecting facets at both ends of the device induces an optical feedback. So in the device that we have seen, I have already told that there is a cleaved structure at the end. Okay, so this is kind of a reflecting structure. So whatever laser action has performed will be reflected back, creating a resonant cavity, which is the basic requirement for a laser. And the reflectivity of this cleaved structure, so this is called as a cleaved structure. So reflectivity of one side of the cleaved structure will be around 100%, other side will be around 95%, so that some amount of light can be obtained out. If a net optical amplification is large enough to compensate for all possible optical losses, photons oscillating back and forth form a steady state electromagnetic wave, which finally emerges out of the laser device as a coherent optical beam. We have seen that the principle in which the lasing action should take place is whatever gain is there, that should be equal to the loss. So whenever the gain and loss becomes equal or the gain crosses loss, then there is a steady state in which you will have a lasing action. And once you have the lasing action, laser output can be taken out. Okay. So that's regarding the working. Now, if you look at some of the characteristics of this indium gallium nitride laser diode, you see that this is current versus output power. So as the current increases from 0 till around 1.7 amps, the output power has a very small change. Okay, very small change. It's just a normal linear change, which is of not much use for us because we need maximum output for power for low values of current. At 1.7 amps, you see there is an exponential change. That means if you take up this, it might be around 2.25. Within a change of 0.525 amps, you see that the optical power generated has changed from 50 milliwatt to 200 milliwatt, which is a 150 milliwatt change. But between 0 and 1.7 watt, there is a change of only 50 milliwatt. So this 1.7 amps is the threshold current. So after the threshold current, there is a huge change in the output power. Also, the quantum efficiency is about 13%, and the pulse output power is around 215 milliwatt at 2.3 amps. So this will be around 2.3 amps. If you look at that, this is around 213 milliwatt. Okay, so this is the current and power characteristics. If you look at the wavelength of the emitted light, you see that. So this is for 1.3 amps injected current. This is for 1.7 amps injected current. This is for 2.1 amps injected current. So if the at injection currents below the threshold, spontaneous emission appeared with full width of half maximum of 20 nanometer and a peak wavelength of 410 nanometer. Actually, this FWHM we have already seen. If you are known, this is the line broadening spectrum. So this is the line width we have seen, which is delta nu. This is actually the full width at half maximum. Okay, this is the full width, and this is the half of the maximum values. This is 1 by 2. This is called as full width half maximum. So below the threshold, you see the full width half maximum is around 20 nanometer at a peak wavelength of 410 nanometer. So this is that scenario. So the peak wavelength is 410 nanometer, and the full width half maximum is 20 nanometer, which is very low. Now, as you increase the threshold current, a strong stimulated emission at 470 nanometer with full width half maximum of 1.6 nanometer was the dominant emission. So when you go higher with injection, you see that around 2.1 amps, the wavelength emitted is around 470 nanometer, and you have a high intensity. Okay, so as you increase the current, your wavelength changes from 410 to 470 nanometer, so as the intensity of the current. Okay, the next characteristic is current versus voltage, forward voltage. So if you look at the graph, you see that up to here there is a small change, or you can say that there is the slope is pretty high, and after this the slope is almost constant or a linear one. Okay, so you can say that our operate threshold current was something around 1.7, which is here. So voltage corresponding to that threshold current is approximately 34 volt. Okay, so this is the region in which the laser diode should be operating. So operating voltage of the device at this threshold current should be around 34 volt. Okay, and so that's about our laser diode. And I have taken this from the book by Nakamura. So he was the inventor of this device. So if you want to refer, or if you want to look at further on this one, you can refer the book. And also there's a PhD dissertation by Thomas, which I have taken to look at the reference. Okay, so that's about the our laser diode, which is indium gallium nitride laser. Basically, you should be able to know the construction and working of the laser. That is very, very important in an exam point of view. And then you should look at the properties, which is basically the threshold current and all these things. So that will give you a idea on how the laser works. Okay, fine. So let me take the attendance. I'll call the numbers. You can just tell your present or not present. Okay. So I'll call up EC1 first. Just a second. Okay. EC1, Aishwarya, if you're there, you can just unmute your mic and